Okay, this is group activity 7. And I'm going to go through it in some detail. You have the solutions already, but I'm going to go over them. So you have a bacterial culture produced 41.3 milliliters of methane gas, 31 degrees C, 750 millimeters of mercury. What is the volume of methane at standard temperature and pressure? Okay, so you can make a list here because you always, with these gas problems, you have a lot of information, so it's good to write it down and organize it. So the culture produces methane gas, and the volume V1 is 41.3 milliliters at a temperature T1 of 31 degrees C, and pressure P1 is 753 millimeters of mercury. Okay, then it's going to be converted to standard temperature and pressure conditions. And so we want to know what the new volume is going to be. Okay, so V2 is what we're looking for. T1 is going to be equal to 273.15 Kelvin. This is by definition. Okay, standard temperature. And standard pressure, whoops, this is T2, sorry. And then P2, which is the standard pressure, which is 1 atmosphere, as many zeros, 0.000 as you need. All right, so we're going to solve for V2, put it into the equation. P1 V1 over T1 is equal to P2 V2 over T2, right? Solve for V2 here, so this will be equal to T2 P1 V1 divided by P2 T1 is equal to V2, okay? And now we just have to make sure that the units are the same. So for volume, you have milliliters and you're solving. You could solve in milliliters. That would be okay here. This is not a PV equals nRT equation. If it was, you'd have to have it in terms of liters. Okay, so temperature then is in degrees C. This is in degrees Kelvin. So they have to be the same. In fact, both have to be in Kelvin. So you want to add 273.15 to get the Kelvin degrees, and that's 15. And let's see, 3, 4, 7, 3 is 10, so 304. 0.15, you don't even need that, 0.15 degrees Kelvin. Okay, then you have pressure. P2 is in atmospheres, P1 is in millimeters. Convert this one to atmospheres. You can do it either way, but it doesn't really matter. So you want to say that there's 760 millimeters of mercury for every 1 atmosphere. So basically you divide that number by 760, right? And get my calculator here. Calculator's not working. Okay, hold on. Whoops, there it is. Okay, so we got 753 millimeters divided by 760 millimeters. So that's 0.991 atmosphere. So it's not a big change in pressure, but the temperature has a difference of 31 degrees. All right, so I'm just going to plug it all in. And let's go ahead and rewrite it here. V2, T2, P1, V1 divided by P2, T1. So V2 then will be equal to 273.15 Kelvin multiplied times P1, which is 0.991 atmospheres, divided by multiplied by V1, which is 304 Kelvin. Wait a minute, that's not right. Yeah. V1, sorry, 41.3 milliliters. Okay, temperature, pressure, volume, okay. And then divide by P2, which is 1 atmosphere. And then divide by 304 Kelvin, like that. So V2 will be equal to 273.15 times 0.991 times 41.3 divided by 304. So it's 36.8. And you got milliliters because Kelvin cancels and atmospheres cancels, and you have milliliters. Okay, so that's the first one. All right, so the second problem, this was number 1. This is number 2. So let's see if we can read that. Partial pressure of methane is 0.175 atmospheres and O2 is 0.250 atmospheres in a mixture of the two gases. What is the mole fraction of each gas in the mixture? That's part A, and then we'll do part B and C. So the mole fraction is defined as, for example, you have methane. Methane has the chemical formula CH4. So this would be equal to the moles of CH4 divided by the total moles, which is the moles of oxygen plus the moles of CH4. And but you are given, instead of moles, you're given pressures, because there's two definitions for mole fraction. So you could use PV equals nRT and go back and forth between these two expressions. But it would be the pressure, this is the partial pressure of methane, divided by the total pressure. Okay, and total pressure, yeah, okay, hold on. Yeah, so you have to add them up. Okay. All right, so the pressure of methane that's given is 0.250, and that's atmospheres. And then you're going to divide by the total, so it'll be 0.250 atmospheres plus the other one, which is 0.175 atmospheres. All right, and then that will be equal to, let's see, 0.25 plus 0.175 divided by 0.25. Take the reciprocal of that. So that's going to be 0.588. And remember, there's no units for mole fraction. Okay, atmospheres cancel. Then you would do the same thing for the oxygen. So mole fraction of oxygen is, this time the moles are 0.250. So 0.250 atmospheres divided by the total pressure, which is 0.250 atmospheres plus 0.175 atmospheres. So that then would be equal to 0.412. Okay, no units. Now let's see, the original problem did have 3 sig figs, so it would be appropriate to have 3 sig figs here. Okay, so that's part A. What's the mole fraction? Part B, if the mixture occupies a volume of 10.5 liters at 65 degrees C, calculate the total number of moles in the gas. Okay, so you've got P total is equal to P methane, partial pressure of methane plus the partial pressure of O2. So that's the total pressure. And let's see what else. You could do that to calculate the total. Yes, you could use PV is equal to nRT. You could use P total, and then that would be equal to N total. Let me rewrite that. P total times volume is N total RT. So it's the ideal gas constant with using the total amounts. Okay, so then we are solving for the N total, number of moles. So N total is P total times V divided by RT. So N total is equal to P total, which is 0.175 atmospheres plus 0.250 atmospheres. The volume is 10.5 liters. The temperature, well, R is 0.08206 liter atmosphere per mole per Kelvin. That's the ideal gas constant in liter atmospheres. And then the last one is temperature, which is 65 degrees C plus 273. That was multiplied, sorry. 65 plus 273.15 is 338.15. I left it out. Okay, that ought to do it. So 0.175 plus 0.25 equals 0.425 times 10.5 liters divided by 0.08206 and divided by 330, that's an 8, 338. And that's going to be equal to 0.161 moles. And let's see if 3 sig figs are still appropriate. The answer is yes, they are. This is an 8 right here. Whoops. Okay, so then I'm not checking the answers, but I think let me go down and check the answer on that one. Yeah, yep, so far so good. Okay, and then go back up to part C. And for part C, calculate the number of grams of each gas in the mixture. So you would have to take the moles of each and use molar masses to convert to grams. You have to get the moles of each one. So you could take, each pressure and do this calculation to get, and like the first one is for the methane, right? So then you could take 0.175 and just cross this out and recalculate the whole thing, and that would be the moles of the methane. And then to get the moles of the oxygen, just leave that one out and use that to calculate the moles of methane. And there's another way to do it too, which is, let's see, think about it here. So total pressure times the mole fraction of methane will be equal to partial pressure of methane. Okay, that's true, but there's also another equation that the moles of methane are equal to the total number of moles multiplied times the mole fraction of methane. So you could use either one, but you don't end up with what you're looking for here, the methane. Here you'd have to use PV equals nRT again to get moles. But the second version of the equation, ratio of moles rather than ratio of pressures, works. So you have N total from part B here. So the moles of methane are going to be equal to 0.161 moles total multiplied times the mole fraction of methane, which is 0.588. Okay, and then you have 0.161 times 0.588, and this one is 0.0946 moles CH4. And then if you want the mass of methane, you take the moles and divide by multiply times the molar mass. So 0.0946 moles of methane, CH4, multiplied times the molar mass, which is C12, 16.04, I think that's right, grams per mole, grams methane per mole of methane. Okay, and so that'd be times 16. So this is going to be 1.52 grams of methane in that mixture. Then you would say that the mass of the O2 is going to be, nope, we're not there yet, hold on. We would say that the moles of O2, so moles of O2 will be equal to N total times the mole fraction of O2, and N total is 0.161 times the mole fraction of O2, hold on, mole fraction of O2 is 0.412, whoops. And that's equal to, let's see, 0.161 times 0.412. And this is 0.0663. Okay, and this is moles of O2. And then mass of O2 is equal to 0.0663 moles O2 times the molar mass, which is 32 grams O2 per mole of O2. So 0.0663 times 32 equals 2.12 grams of O2. Now let's part C. Okay, so then we have number 3. And number 3 is a reaction of butane plus oxygen. So it's 2C4H10 in the gas phase plus 13 O2s in the gas phase forms 8 CO2s in the gas phase and 10 waters in the gas phase. Okay, and just leave the phases out. You don't need them really to do the problem, so it's too much stuff to write down. All right, you're given these two reactants, methane and O2. You're given quantities of both. It happens to be in the form of PV equals nRT for each one, and that's why it's a longer problem, but it's the same basic limiting reactant problem where you're given quantities of both reactants and you got to figure out which one is going to dictate how much product's going to be formed and how much of the excess is left over. So it's just like what we did before, except it's harder. But I like to make a list here, and we have for the butane. Butane, by the way, is in like your butane lighter. So you have volume is 4.50 liters, temperature is 273 Kelvin, pressure is 1 atmosphere, and it's reacted with volume is 20 liters of oxygen, temperature is 300 Kelvin, and pressure is 0.91 atmosphere. Okay, so we're going to get moles for each one of those. And then from there we do the limiting reactant problem. So we're going to look for PV is equal to nRT. N will be equal to PV divided by RT, right? So N is going to be equal to 1 atmosphere, volume 4.50 liters, R is 0.08206 liter atmosphere per mole Kelvin, and the temperature is 273 Kelvin. So that would be the first one. The second one, N, would be equal to pressure, which is 0.91 atmospheres. Pressure times volume, PV, divided by RT. So volume is 20 liters. R is 0.08206 liter atmosphere per mole Kelvin. And then the temperature here is 300 Kelvin. All right, so then let's calculate moles. So moles for butane C4H10 and moles for O2. Okay, so the butane is 4.5 divided by 0.08206 and divided by 273. So this is going to be 0.201 moles of butane. And the oxygen would be 0.91 times 20 divided by 0.08206 and divided by 300. So we've got 0.739 moles of the oxygen. All right, now the next step is to figure out which one is the limiting reactant. And the problem is asking what's the pressure of carbon dioxide and water, so both products here. And then for the total pressure, you're going to have to get the leftover reactant and add that in there as well. So first we just want to get the pressures of CO2 and water. You can pick either one. Let's go ahead. Let me actually go to the solution here and see, use the numbers that I had here. Moles of O2. Okay, so next then is the amount of CO2 formed. And so yeah, in the key to group activity 7, I chose to go after the moles of CO2. So let's do that. So you're going to look at the moles CO2, which will be equal to the moles of butane, 0.201. And then you look at the balanced chemical equation, and you want to convert from moles of butane to moles of CO2, and it's an 8:2 ratio. So you want to say that there are 8 moles of CO2 for every produced for every 2 moles C4H10 consumed. Okay, so it's 4 times that will be the moles, so 0.804 moles of CO2 will be formed if C4H10 is the limiting reactant, but let's see, we don't know that yet. And then the second one is the 0.739 moles of O2. And same thing, we're calculating moles of CO2. So there's 8 moles CO2 for every, let's see, 13 moles of O2. Those are the coefficients in the balanced chemical equation. So 8 over 13 times 0.739. And this one is 0.455 moles of CO2 will be formed. So now you want to compare these two, right? And pick the smaller one as the correct answer. So this is the theoretical yield right here for the CO2, 0.455 moles. And therefore, the O2 is the limiting, and this is what we're doing here, we're looking for limiting reactant. The O2 is the limiting reactant because the O2 produced the smallest amount of CO2. Okay, so now we know how much CO2 is formed. We can use the limiting reactant for everything going forward. Okay, so use limiting reactant to get the amount of water. Okay, and that's a 10 to oxygen searching 10 to 13 ratio. Okay. Okay, so you're going to use your limiting reactant, which is O2. So, whoops. 0.739 moles of O2. And you want to look at the ratio of water to O2. And so it's 10 moles of water for every 13 moles of O2. All right, and then that works out to be 0.568. So the moles of O2 cancel and you have moles of H2O. Okay, so that will be the amount formed, 0.568. And that's because the limiting reactant told us that. Okay, next you want to look at use the limiting to get the amount of butane. First you want to calculate the amount that's used up, and then you want to use that to get the amount of butane that's left over. All right, so we're going to take the same limiting reactant, 0.739, and we'll look at the periodic table again to get the amount of butane. And let's go back up there again. You have 2 moles of butane for every 13 moles of O2. And I can see in the key that there's a unit error there. I'm going to correct it right now. So it's a 2 to 13 ratio. 2 moles of butane. Whoops, 10, C4H10 for every 13 moles of O2. The numbers are right, but the unit right here was incorrect. It said water. And so you get 0.114 moles C4H10 consumed. So that means how much was used up in the reaction. All right, let's go over this concept right now. So you calculated the moles of CO2 twice. You picked the smaller number, and from that you learned that the O2 dictated the amount of the smaller number. So this is the limiting reactant. Now you're going to use the limiting reactant. Oops. You're going to use the limiting reactant, which is O2, right? And you're going to figure out how much C4H10 reacted with it. Turns out you've got more than you need of this. This is the one we call the excess reactant. You got more than you need, so how much is left over after the correct amount reacted completely with all of the limiting reactant O2 to form the product. So there's two parts to it. Okay, so you got the next part we're going to use, that's how much is consumed. So now we're going to take the amount that was used up in the chemical reaction and subtract that from your initial amount. So 0.201 moles C4H10 was what you started with after your PB equals nRT. And then you're going to subtract 0.114 moles C4H10 consumed. So right here. And then the difference between them is 0.087 moles butane. Oops, C4H10. That's how much is left over. Okay, now we're not done with this problem. It's really long. And of course, on a multiple choice test, I would break it up into different parts. I wouldn't ask you to go from beginning to end and then choose one answer, you know. Choose 1 out of 4 possible answers as the correct one. So I would break it up. It's worth quite a bit of points because it's pretty long, right? Okay, so now the question is, what's the partial pressures of CO2 and water? And then also we can get the total pressure by adding them together. Okay, so there's a couple ways you could do this, but let's go ahead and use the partial pressures because it's asked for that. All right, so let's see. We're going to get partial pressure of CO2. So that is this amount right here, turned back into pressure. And this is going to be, you're using PV equals nRT, solve for P, so it's nRT over V. And then you have 0.455 moles of CO2. And the rest of it is just constant, so 0.08206 liter atmosphere per mole Kelvin. And temperature is given as 298 Kelvin. And then we're going to divide by the volume, which is 1 liter. And so partial pressure of CO2 is equal to 11.1 atmosphere. Okay, next we're going to look at partial pressure of the other product, which is the water. And we're going to use the moles again. So it'll be 0.568 moles of H2O. And the other numbers are the same, 0.08206 times 298 divided by 1. So partial pressure of water is equal to 11.1. Okay, so we got that. And then we have that leftover methane, which is right there. So we're going to get the partial pressure of CH2 butane, sorry. C4, isn't it? I'm sorry. C4H10. And you're going to use the moles left over, so it's 0.087. And the rest of the numbers are the same, times 0.08206 times 298, dividing by 1. So the partial pressure of butane is equal to 2.13. Yeah, I was starting to say before that we could have added the moles together, this plus this plus this, and then multiplied it times all this rest of this stuff rather than calculating each partial pressure. But the way the question was worded, it wanted the partial pressures. But if you just wanted the total, you could use that other plan. So now you're going to add them up. P total is going to be 11.1. Got another mistake there. This one is 13.9. Okay, so you're going to add 11.1, 13.9 plus 2.13. So P total will be equal to 27.13 atmospheres. All right, so next is number 4. And this problem is a reaction of magnesium nitride and water to form magnesium hydroxide and ammonia. So it's 2 Mg3N2, which is a solid, plus 12 waters, which are liquid, which is liquid, 6 magnesium hydroxide, which is a solid, and 4 ammonia, which is a gas. The phases matter in this one. All right, so we're going to start with 1 liter container, 30 degrees C. You have 4.56 grams of magnesium nitride. The amount of water is 6.92 grams. And in the end, after the reaction, you'll have ammonia gas, and the volume is 1 liter. Temperature is 30 degrees C, 30.0. And one times pressure. So you're going to have to calculate the pressure. Okay, so that's the problem. You're given the mass of this one, the mass of that one. You're going to convert them to moles. Use the mole ratios to figure out how much magnesium hydroxide is formed and how much ammonia is formed. And then one of these will be the excess reaction. We're going to figure out how much is left over of it. And in the end, we'll get the pressure of the ammonia. So it's complicated again. These are long problems. You should be able to do them on your own. Write the problem at the top of the test and then top of a blank paper and go through it. It's complicated. You can see the mistakes that I was making. Okay, so we'll start by calculating the moles of ammonia that are formed. It's a limiting reactant problem. So it's going to be, we will take the amount of magnesium nitride, calculate the amount of ammonia, then take the amount of water, calculate the amount of ammonia. You'll have two values and you're going to pick the smaller one. That's our technique. So you're going to say 4.56 grams magnesium nitride, and convert that. So I have the mole mass here, 100.915 grams magnesium nitride in 1 mole. That's just the molar mass. Okay, now you're going to go to ammonia. So it'll be 4 moles NH3 for every 2 moles magnesium 3 nitride. And we can stop and calculate moles here. We don't have to go all the way to pressure for twice, right? So just go to the moles, 0.0904 moles of NH3. Okay, now take your other quantity, which is water, and calculate the amount of ammonia. So 6.92 grams of water. Use 18.02 grams of water per mole water, so that's the molar mass. Then you're going to use the coefficient for water, for ammonia to water. So it'll be 4 moles NH3 for every 12 moles of water. Calculate that and you get 0.128 moles NH3. Okay, so again, you're going to compare the two and you're going to pick the smaller one. This will be the amount of ammonia formed, and that means that the magnesium nitride is the limiting reactant. Okay, so that's how it's going to be formed. Right, okay, next is the pressure of the ammonia. Right, you've got the amount of ammonia, 0.0904. So the pressure of NH3 that will be formed will be nRT over V. PV equals nRT, right, and solve for P. So the number of moles is 0.0904 moles NH3 times 0.08, 206 liter atmosphere per mole Kelvin. Temperature is 30 degrees, so 30 plus 273, so it's 303. 303 Kelvin. And then you have 1 liter again, so this one is divided by 1 liter. So the pressure here is calculated to be 2.25 atmospheres. that's quite a bit, 2.25. All right, and then part B. So this is part A right there. And part B is to figure out how much water is left over and how much water formed. You can get that from the limiting reactant. All right, so we're going to look for the amount of water that was reacted. So we want to get moles, I believe, moles of water reacted, and then we want to actually convert it to grams. So we're going to use, so we want the mass of the water reacted or used up. And we're going to use the limiting reactant for that. So you have 4.56 grams of magnesium nitride, and with that you're going to multiply. It's a 12:2 ratio, so 12 moles water were used up for every 2 moles of magnesium nitride that was used up on the left hand side of the reaction. So it's a 12:2 ratio. That'll give you moles of water, and to get the mass you multiply times the molar mass, 18.02 grams of water per mole of water, and you get 4.88 grams water consumed. Okay, that's not the answer though. That's how much is used up. Remember, that was the one that's in excess. So you want to start with the amount of water, you want to use the amount of water that you started with, which is 6.92 grams of water. And that's how much you had initially before the reaction. Just say initial, IAL, initial. And subtract the amount was used up, 4.88 grams of water. And then that will be 2.04 grams of water, excuse me. So that is the amount of water that is left over. This is the amount of the excess reactant right here. Well, I think that might be the whole problem. Yep, okay. So then we have problem 5. And problem 5, let me look at that. So you have a reaction that takes place under STP conditions, the reactants and the products for all gases. And the question is, how many liters do you get of the products and how much is left over? So it's another limiting reactant problem. And I think it's a little bit easier because you have the STP conditions. So let's have a look at this. You've got 2 N2H4. Everything's in the gas phase. I'm going to leave that off. Plus N2O4 forms 3 N2 plus 4 H2O, all in the gas phase. Okay, and you have 2.02 liters of N2H4, 2.02 liters of N2H4. You have 1.11 liters of N2O4. So the question is, how many liters of N2? That's part A. How many liters of N2 are you going to get? All right, this one's easy. And you're going to just use ratios of volume, just like you would use ratios of moles. And that's because of Avogadro's law, which says that the volume is proportional to the number of moles. So normally what we do is take the moles of N2H4 and calculate the nitrogen. Then we take the moles of N2O4 and calculate the moles of nitrogen. Pick the smaller one, that's the amount formed, and it goes from there. But because these two are proportional, if you use PV equals nRT, everything would cross out except for the volume. So the ratio of the moles is going to be the ratio of the volumes. So you can just say, you could use the volume 2.02 liters and calculate the volume of N2. Then use the volume 1.1 liters, 11 liters, and calculate the volume of the N2. Pick the smaller of the two, and that would be the volume. And that's because of Avogadro's law. Okay, so that's the plan. We're going to take 2.02 liters of N2H4, and we're going after the N2, so it's 3 liters of N2 for every 2 liters of N2H4. You see what I did there? So 3 liters of N2 divided by 2 liters, so it's a 3-to-2 ratio. Instead of saying moles, you just say volume, right? And multiply it times the N2H4. So you've got 3.03 liters of N2 formed. And also, you have to get the other one. So 1.11 liters of N2O4, 1.11 liters N2O4. And the ratio is going to be 3 liters of N2 for every 1 liter of N2O4. So 3 to 1. 3 liters N2 for every 1 liter of N2O4. So this will be 3.33 liters of N2. So I actually should not have written the word formed at that point. I was just copying it off the key there. The next step here is to compare the two and pick the smallest one, right? So then you're going to pick this one. This is the amount formed, okay? So that's the amount formed. And therefore, this is the N2H4 is the limiting reactant, okay? So part A, we know how many liters of N2 are formed. The answer is 3.03. Okay, so that's part A. And this one's easier because that relationship between volume and moles. And then the next part's kind of interesting too. You want your excess N2O4. You're going to use your limiting reactant again to calculate the amount of N2O4 used up. I think that's it. Yeah, that's the end of that problem. Okay, so we're going to use